Hey everyone, welcome to this episode of Quantum Computing Podcast. In the last video, we were just finishing up page number 13. We ended just above exercise 1.2.7. So let's get started from there. Actually, this exercise and the exercise on the next page are actually very, very trivial. Let's do that. All right, so it says that for any complex number, there's ordered list of 0, 0 is nothing but the additive identity. Okay, so you can add 0, 0 in any order and actually get the same complex number back. It's actually very intuitive, but also very, very trivial. So let's say C is an ordered list of two real numbers A and B, right? And if we add C to 0, 0 or 0, 0 to C first, which will give us A plus 0, B plus 0, which is AB, which is C, right? And it's true other way around as well. If we add C to 0, 0, we get the same number. So this is nothing but exercise 1.2.7. As I said, very quick, very easy. And the next one is page number 14 actually, is exercise 1.2.8. So this is also can also be done in a very, very similar manner. So 1, 0 is a multiplicative identity. So let's say if it's the same complex number, an ordered list of A and B are real numbers, as we know. If we multiply C with 1, 0, you might remember the multiplication formula, right? It's a1 into a2 minus b1 into b2, and then a2 into b1 plus a1 into b2. So here it would be a into 1 minus b into 0, and then b into 1 plus a into 0. So that will actually give us a and b, which is nothing but c. And you can do this in a reverse manner as well. 1, 0 multiplied by c. I'm using asterisk as the multiplication sign here just for the quicker way of doing multiplication, but we know that cross is a sign of is a notation to do multiplication in the complex number world, and you also get c back. It's very easy to do. Yeah, you can also check your answers at the back. I think there are no answers for these two exercises because they are very easy to do. All right, so let's move on. So next, actually, a few lines and a couple of paragraphs are nothing but they talk about the properties of complex numbers. So there are 7 properties listed here that we have identified so far, and the argument that authors make that this is nothing but the definition of field. This is an algebraic term, not necessarily going to be useful in understanding the quantum computing, but it's still good to know that this is a field, and R is a subset of C. Now this is very intuitive to understand, right? Because C is nothing but the ordered list of real numbers. So R just makes sense to be subset of C because C contains everything that R contains, right? Because it's the ordered list of two real numbers. And one thing that we noticed actually on page number 9, so it could be video 2 or video 3, that the polynomial equations with complex coefficients have solution in C itself. So they have the complex solution. So that actually makes C algebraically complete or algebraically closed set. So let's check page number 9. Yeah, right here, actually, I actually made a comment there that C is algebraically closed when I was explaining that polynomial of n degrees have n roots. Okay, so that shows you that the set of complex number C is very important, right? It's really important a very unique set of numbers actually. And what is this? Okay, so this paragraph actually talks about that there are three ways of changing the signs of complex numbers. Okay, if it was just a real number, there is just one way to change the sign, which is just change the sign. So if we are talking about 2.3 as a real number, the only way to change sign is just change the sign from positive to negative, which is minus 2.3. If it's minus, I don't know, minus 1.1, then change the sign and make it 1.1. But for the complex numbers, as it's again an ordered list of two real numbers, there are three ways to change the sign. Either change the sign of the real part, change the sign of the imaginary part, or change the sign of both the parts. Well, the fourth option is not to change signs of any of the parts, which is not doing anything. So there are actually three ways of changing the signs. And how do we change the sign? We just multiply that complex number with this minus 1, 0, the order list of minus 1, 0. Exercise 1.29 just says that verify that, is it true or not? Again, very trivial. Take C as an order list of A and B real numbers. Multiply that with minus 1, 0, and then you get minus A minus B. Okay. So we just changed the signs of both real parts and imaginary parts. And if we just change the sign of the imaginary part, then that operation is called conjugation, and the result is called complex conjugate of that number. So if the number is a plus bi, and then if we just change the sign of imaginary part, which is b, then we get a minus bi. So a minus bi is a complex conjugate of a plus bi. A plus bi is a complex conjugate of a minus bi, and they are complex conjugates of each other. And one way to denote this is C bar. Okay. And I think, so there is a reference actually here on page 9. You might remember in this exercise 1.1.4, I said that if you are verifying minus 1 plus I is a solution, which we did, I said that why don't you verify minus 1 minus I is also a solution of this polynomial equation, which it is actually. If you followed it, you would have found that it is actually a solution. So minus 1 minus I is actually the complex conjugate of minus 1 plus I. And the reason this is also a solution is the roots, actually the solutions, come in pairs. So both the complex conjugates are the roots of this polynomial equation. All right, coming back to the end of page number 14, it says that changing the sign of just the real part. Okay, so if a plus bi is the complex number, then just changing the sign of a, which would make it minus a plus bi, has no real name in this context. Okay, that operation doesn't have the real name, but it can be seen as this notation. So C bar is nothing but the complex conjugate, and if you multiply this with minus 1, 0, then it becomes minus C bar, which actually just is nothing but just the change of sign of the real part. Okay, so why and how? Let's look at this example. This could also be an end of this video, and we'll pick it up from page number 50 next time. Okay, so let's say C is an order list of A, B, okay, which makes C A plus BI. Right? We all know that by now. So C bar is nothing but A minus B, right? It makes it A minus BI. Now minus C bar, which is nothing but minus 1, 0 multiplied by A minus B. Now we know from this exercise 1.2.9, right here 1.2.9, that if we multiply any complex number with minus 1 0, it changes the sign of real and imaginary components of this complex number. So a and minus b both get flipped, and they get flipped to minus a b. Okay, minus a b is nothing but and it doesn't have a real name, but it actually is nothing but it has the same sign and the number as imaginary number as c, but the sign of the real number is flipped. Okay, so this is minus c bar, and that's what this paragraph was saying, that converting c to minus c bar has no particular name, at least in this context. And there are a couple of other exercises on page number 15 that gives you some important properties. All right, so you know what, I know we are right on page, more than 10 minutes into this video, but let's go through this two exercises real quick. All right, so c1 bar plus c2 bar is equal to c1 plus c2 bar. Okay, so if yeah, I actually did it right here, so let's just follow it. So if let's say c1 is an ordered list of a1 b1, c2 is an ordered list of a2 b2, then c1 bar is a1 minus b1, c2 bar is a2 minus b2. Remember that whenever we have bar, which means the sign of the imaginary part is changed and nothing else is changed. So if we add these two numbers, we get a1 plus a2 minus b1 minus b2. Simple. Now let's look at the other side of the equation, which is c1 c2 bar. So if we just do c1 plus c2, c1 plus c2 bar, c1 plus c2, then it's a1 plus a2 comma b1 plus b2. Simple enough. And if we make the complex conjugate of this result, which is c1 plus c2 bar, then the real number stays the same, and only the sign of the imaginary number changes, which is minus b1 minus b2, and these two are same. So simple, very, very simple. And the next exercise is it's the same exercise, but with respect to multiplication. Okay, so multiplication of c1 bar with c2 bar is nothing but the bar of c1 multiplied by c2. Actually very easy to follow. Same c1 c2, if we have c1 bar multiplied by c2 bar, these two numbers, then we get a1 into a2 minus minus b1 into minus b2, which is b1 into b2, and then a1 into minus b2, which makes us minus a1 b2, plus a2 into b1, which makes it minus a2 b1, and then go to the other side of the equation, which is do this multiplication first and then make the complex conjugate, and these two are same. Okay, all right, so we'll end here, and then we'll pick it up we will pick it up from here in our next video. Thank you.